Right now, beneath one of the most photographed places on Earth, something is moving, and the data coming out of the Aegean is making volcanologists genuinely uneasy. Santorini. The name alone carries a certain weight. It conjures whitewashed walls and blue domes and honeymoon photographs, and the kind of sunsets that make people restructure their entire understanding of beauty. It is, by most measures, the crown jewel of the Greek islands, and one of the most visited tourist destinations on the planet, drawing somewhere between 2 and 3 million visitors every single year. A place that feels, in the imagination of most people who go there or dream of going there, like the safest, most idyllic spot in the Mediterranean. Except that Santorini is not a place. Not exactly. It is a caldera, the exposed rim of one of the most violent volcanic systems in the recorded history of the Northern Hemisphere. And in recent months, the instruments buried in the seabed around it, the sensors drilled into its rock, the satellite data processing above it, they have all started telling a story that scientists are watching with the kind of focused, careful attention that tends to precede very serious conversations. What is happening beneath the Aegean right now? What is Colombo, the hidden submarine volcano sitting just 6 kilometers off Santorini's northeastern coast, actually doing? And what could it mean for the 2.8 million people who live, work, and vacation in its shadow? Those are the questions this video is going to answer, and some of the answers are going to surprise you. Most people, when they hear Santorini, picture whitewashed walls, blue-domed churches, and a glass of wine at sunset over a caldera, and that caldera is the entire problem. Let's establish what we're actually looking at geographically, because the scale of this system tends to get lost in the aesthetics. Santorini, officially called Thera, sits in the southern Aegean Sea, roughly 200 kilometers southeast of Athens. The islands that form what tourists call Santorini are not a natural archipelago. They are the broken, surviving rim of a massive volcanic caldera, a circular depression formed when a volcanic system erupts so catastrophically that its own magma chamber collapses inward. The lagoon in the center, the one the cruise ships sail into, the one visible in every aerial photograph, that is the caldera itself. You are sailing into the remains of one of the most powerful eruptions in human history. That eruption, the Minoan eruption, dated by researchers to roughly 1600 BCE, give or take several decades, is estimated by volcanologists at institutions including Oxford University and the Smithsonian Global Volcanism Program to have had a volcanic explosivity index of 7. To put that in context, the 1980 eruption of Mount St. Helens, which killed 57 people, flattened 230 square miles of forest, and sent ash across the continental United States, was a VEI 5. The 1991 Pinatubo eruption in the Philippines, which temporarily cooled global temperatures, displaced hundreds of thousands of people, and is considered one of the largest eruptions of the 20th century, was a VEI 6. The Minoan eruption was an order of magnitude beyond that. It is widely believed by researchers to have contributed, possibly significantly, to the destabilization and eventual collapse of the Minoan civilization on Crete. It sent tsunamis across the eastern Mediterranean. It deposited ash layers across an enormous geographic footprint stretching from Egypt to the Black Sea. And it did all of this from the exact same volcanic system that, today, roughly 2.8 million people are embedded within, residents of the surrounding islands and mainland Greek coast, plus the enormous seasonal tourism population that floods in each summer. Now here's what makes this situation particularly complex. When most people think about volcanic risk at Santorini, they think about the Kameni volcanic field, the cluster of volcanic islands that sits right in the center of the caldera, the small dark islands you can see from the rim. Nea Kameni, the younger island, last showed significant activity in 1950. There are ongoing low-level hydrothermal emissions from it. Scientists at the National Observatory of Athens monitor it continuously. It is, in the language of volcanology, a known and actively watched system. But Colombo is a different conversation entirely. About 6 kilometers northeast of Santorini's coast, hidden under roughly 500 meters of Aegean water, sits a volcanic cone that has been quietly studied by researchers from institutions including the University of Rhode Island, INGV in Italy, and the Hellenic Center for Marine Research. And what they've been measuring in recent years is deeply unsettling. Colombo is not a new discovery. Volcanologists have known about it for centuries, in the sense that it erupted violently above the waterline in 1650 CE, We'll get to that. And its existence as a submarine structure has been documented scientifically for decades. But the level of detailed monitoring and the quality of data being collected from Colombo has improved dramatically over the past 10 to 15 years, and what that improved data is revealing has pushed the volcano considerably higher on the watch list of European hazard researchers. Here's the geological context you need. The Aegean Sea sits in one of the most tectonically active zones in Europe. The African tectonic plate is pushing northward and subducting, sliding beneath, the Eurasian plate along a collision zone that runs through the Mediterranean. This subduction process is what drives volcanism across the entire Hellenic volcanic arc, a chain of volcanic centers that includes Santorini, Milos, Niceros, and several other islands. The geological stress that this creates is not abstract background noise. It is active, measurable, and ongoing. Colombo sits directly on this system. Its cone rises approximately 500 meters from the seafloor, meaning its summit is currently about 18 meters below sea level. It is not a small structure. Researchers mapping it with multi-beam sonar technology have found that its caldera is approximately 1.5 kilometers in diameter, with a hydrothermal field on its floor that vents gases including carbon dioxide, hydrogen sulfide, and, critically, sulfur dioxide. The concentration of carbon dioxide measured at the vent field by researchers from the Proteus Project, a collaborative deep-sea monitoring initiative, is among the highest recorded at any submarine volcanic system in the Mediterranean. But here's where it gets complicated in a way that deserves careful attention. Submarine volcanoes don't just threaten through eruption, they threaten through mechanism. Because Colombo sits beneath 500 meters of water, any eruption it produces, if powerful enough to breach that depth and pressure threshold, would interact with seawater in a fundamentally different way than a land eruption. The contact between rising magma and that volume of water can produce what volcanologists call phreatomagmatic explosions, steam-driven blasts that are, in some scenarios, considerably more violent than a standard magmatic eruption would be. The steam expansion is almost instantaneous. The energy release is enormous. And there is a second mechanism that submarine volcanic systems like Colombo carry that makes coastal hazard researchers particularly alert, one that connects directly to the tsunami risk for the surrounding coastlines. The flanks of submarine volcanoes are, in many cases, geologically unstable. Material builds up on steep slopes under high hydrothermal stress, with gas-saturated sediments and weakened rock structures. If a volcanic event, or even a sufficiently large earthquake in the right location, were to trigger a flank collapse, the volume of material displaced into the water column could generate a tsunami with very little warning time for surrounding coastline. Researchers modeling this scenario for Colombo, including work published in geophysical journals and summarized in hazard assessments by the European Geosciences Union, have noted that the northeast coast of Santorini, the island of Ios, and the broader southern Cyclades could be reached by waves within minutes. Not hours. Minutes. Scientists at the Hellenic Center for Marine Research have been deploying bottom pressure recorders and seismic sensors in the Colombo area to try to build the kind of real-time monitoring network that could provide even marginal additional warning time. It is important work. It is also, by the researchers' own descriptions in published literature, still incomplete relative to the scale of the potential hazard. Now, and this is a point worth sitting with, none of this means an eruption is imminent. Scientists are explicit about that. Colombo may remain in its current state for decades. Volcanic systems operate on timescales that humiliate human prediction. What the data represents is a system that is active, that is being carefully watched, and that has demonstrated in the historical record, quite vividly, what it is capable of. To understand what Colombo is capable of, you have to go back to September 1650, a date that doesn't appear in most Western history books, but one that fundamentally shaped the Eastern Aegean for a generation. In the late summer of that year, the sea northeast of Santorini began to behave strangely. Fishermen working the waters reported unusual wave patterns, discoloration of the sea surface, and a smell. Sulfurous, heavy. The kind of smell that old sailors associated with divine punishment rather than geology. Contemporary accounts preserved in Greek Orthodox Church records and in Venetian administrative documents from the period describe the sea in the Colombo area as churning and steaming for days before the main event. On September 27, 1650, Colombo erupted. Contemporary accounts. collected and analyzed by Greek historians and later by volcanological researchers, including work summarized by the Smithsonian Global Volcanism Program, describe the eruption as catastrophic in scale. The explosion was heard, according to reports, as far away as the Dardanelles, hundreds of kilometers to the north. The eruption column rose high enough to be visible from much of the southern Aegean, and the tsunamis it generated, multiple waves, according to surviving accounts, struck the eastern coast of Santorini with devastating force. The recorded death toll from the 1650 event varies across sources, but historical accounts suggest approximately 70 people were killed directly on Santorini by the tsunami impacts and by what researchers now believe were dense volcanic gas clouds, primarily carbon dioxide and sulfur dioxide, that rolled across the water surface and suffocated people and livestock on the island's lower eastern shoreline. An entire herd of cattle on the eastern coast, according to one Venetian-era account, was found dead without visible injury. Cons extent with what we now understand about carbon dioxide asphyxiation in enclosed or low-lying areas. The volcanic cone that erupted in 1650 broke the water surface and formed a temporary island, a small, smoking landmass that existed briefly before subsiding back beneath the Aegean within a few years. What it left behind was a newly enlarged caldera on the seafloor, a dramatically altered hydrothermal system, and a community on Santorini that had been given a very visceral reminder of what the waters around them were capable of. Now here's the comparison that matters. In 1650, the population of Santorini and the immediately surrounding islands was a few thousand people at most. The economy was agricultural and maritime. There was no tourism infrastructure, no international airport, no dense seasonal population, no cruise ship terminal processing thousands of visitors per day. There were no underwater data cables, no submarine power infrastructure, no coastal hotels built at sea level with floor-to-ceiling glass views of the caldera. Today, the picture is almost incomprehensibly different. Santorini's permanent population is approximately 15,000 people, but in peak summer months, the total population on the island swells to over 30,000. And the annual visitor count has, in recent years, reached numbers that have forced the Greek government to begin implementing tourist caps because the infrastructure simply cannot handle the load. The island of Ios, which sits directly in the southern Cyclades and would be among the nearest affected islands in many Colombo scenarios, has its own seasonal population surge. The broader zone within a meaningful tsunami travel radius, including the Turkish Aegean coast, the Dodecanese Islands, and coastal Crete, encompasses a permanent and seasonal population in the millions. The 1650 eruption killed dozens. The system that produced it is still active beneath the same water. That is the then versus now comparison that volcanological hazard assessments are built on. The Hellenic Unified Seismological Network, which operates dozens of monitoring stations across the Aegean, has been logging data from the Santorini-Colombo volcanic field that, depending on which researcher you ask, ranges from worth watching carefully to actively concerning. Let's talk about what the instruments are actually saying. In 2011 and 2012, the Santorini volcanic field experienced what scientists called an unrest episode, a period of elevated seismic activity, ground deformation measurable by GPS monitoring stations, and increased hydrothermal emissions that represented the most significant signs of system activity in decades. During that episode, the GPS network maintained by the National Observatory of Athens and international partner institutions recorded ground uplift in the caldera area. The ground was rising, indicating movement of material at depth. Seismometers recorded thousands of small earthquakes in swarm patterns. The alert level was elevated. Scientists were direct in their public communications that the system was showing unusual behavior. That episode subsided. The unrest quieted. But researchers studying it, including work published in journals including Nature Geoscience and Geophysical Research Letters, noted that the episode demonstrated the speed with which the Santorini system can transition from apparent dormancy to measurable, significant unrest, and they flagged the importance of maintaining and expanding monitoring infrastructure precisely because the warning window, if the system were to move toward eruption, might be shorter than previously assumed. Since that 2011-2012 period, monitoring has continued, and the Colombo-specific dataset has grown considerably richer as new seafloor instruments have been deployed. What researchers have documented at Colombo's hydrothermal vent field includes episodic increases in gas flux, particularly carbon dioxide and hydrogen sulfide output. and seismic activity patterns that indicate ongoing magmatic processes at depth. A 2022 research expedition using remotely operated vehicles documented the vent field in detail, and the findings, reported through the Santorini project, a European Research Council-funded initiative specifically focused on Santorini Colombo hazard assessment, confirmed that the system remains volcanically active at a level that warrants continued close monitoring. It's worth being clear about what active monitoring means in practical terms for the people who live there and the tourists who visit. Greece operates through the National Observatory of Athens, a volcanic alert system for Santorini. The island has evacuation plans, routes are designated, ferry protocols exist, coordination frameworks between local authorities and the Hellenic Coast Guard have been established. Civil protection agencies are aware of the hazard. This is not a system being ignored, but researchers associated with the Santorini project and with related European hazard programs have been candid in published work and public presentations about gaps, specifically around submarine monitoring density, around tsunami warning system coverage in the southern Aegean, and around the public communication challenge of maintaining appropriate awareness in a location whose entire economy is built on being perceived as desirable and safe. There is an inherent tension there that emergency management scholars have written about extensively. The economic incentive to minimize public discussion of hazard risk in tourism-dependent communities is real, and it shapes everything from infrastructure investment to public preparedness messaging. The question isn't whether scientists are watching, they are. The question is whether the watching is sufficient, and whether the communities within the hazard zone have the information and preparation they need. Models developed by researchers at institutions including the National Observatory of Athens and collaborative EU-funded hazard programs have mapped out what escalation could look like, and the scenarios, even the moderate ones, are striking. Let's be precise about what we're doing here. We are not predicting an eruption. Scientists cannot do that with any reliability, and anyone who tells you otherwise is not representing the science accurately. What hazard modeling does is take the known characteristics of a volcanic system, its history, its current state, its geological structure, and ask, if this system were to move toward eruption, what might the cascade of impacts look like? That kind of scenario modeling is the foundation of emergency preparedness. It's how you build evacuation routes before you need them. A moderate eruption scenario at Colombo, one comparable in scale to the 1650 event, could, according to hazard assessments, produce several simultaneous and interacting threats. The most immediate would be tsunami generation. Models suggest that a 1650 scale event could produce waves reaching the eastern coastline of Santorini within roughly 5 to 10 minutes of initiation, before any automated warning system currently in place could guarantee a full population alert and response. The tsunami threat would extend across the southern Cyclades within 20 to 30 minutes, potentially reaching the northern coast of Crete within an hour. The Turkish Aegean coast, home to major resort towns and cities, sits within the broader impact zone in larger scenarios. Simultaneously, any eruption column reaching the atmosphere could disrupt air traffic across a significant portion of the eastern Mediterranean. The 2010 Eyjafjallajökull eruption in Iceland, a far smaller event in terms of geological power, disrupted European air travel for days and caused an estimated €1.3 billion in losses to the aviation industry. A more powerful Aegean eruption could produce a comparable or more severe aviation impact, affecting routes between Europe, the Middle East, and Asia. The gas hazard is a separate and often underappreciated threat. Colombo's hydrothermal system already produces carbon dioxide in significant volumes at the sea floor. In an escalating eruption scenario, the volume of volcanic gases released could produce dangerous concentrations at sea level across the surrounding water surface, a phenomenon that would threaten marine traffic and could affect low-lying coastal areas depending on wind conditions. In a larger scenario, one approaching the scale of the historical Minoan eruption, which researchers are careful to note, could happen at some point on a geological timescale, though there is no evidence of it being imminent. The potential consequences extend to regional agricultural disruption from ash deposition, long-distance tsunami impacts across the entire eastern Mediterranean basin, and atmospheric effects influencing European climate patterns. These are long-range, low-probability possibilities on any human timescale, but they are part of the honest scientific picture of what this system is ultimately capable of. What's important to hold on to here is that the moderate scenarios, the ones actually within the plausible near-term range that hazard planners work with, are themselves serious enough to demand attention. A 1650 scale repeat event in today's densely populated, economically interconnected Aegean would be a crisis of a different order entirely than the one recorded in church documents and Venetian archives. Here's the thing about Santorini. It has erupted before, it will erupt again, and the gap between those two facts is where 2.8 million people currently live, work, and vacation. That's not a statement designed to alarm you into not going to Santorini or into thinking the island is about to explode next Tuesday. It's a geological reality, and understanding geological realities is the beginning of intelligent response to them. The researchers monitoring Colombo and the Santorini caldera are not panicking. They are watching, measuring, publishing, and pushing for better monitoring infrastructure. That work matters. What this video has tried to do is give you an honest picture of a system that most of the world, including frankly, most of the tourists who photograph it every summer, does not understand at all. The caldera is not a backdrop. The submarine volcano 6 kilometers offshore is not an abstract geological curiosity. They are active components of one of the most significant volcanic complexes in Europe, sitting in the middle of one of the world's most visited coastlines. The 2011-2012 unrest episode showed how quickly conditions can shift. The 1650 eruption showed what Colombo can produce. The monitoring gaps documented by Santorini researchers show where the preparedness picture still has real holes. That's the uncomfortable overlap between what we know this system can do and what we've actually built in terms of warning capacity and public awareness. The good news, and there genuinely is good news here, is that the scientific community is not asleep on this. European research funding through programs like the ERC has gone specifically into Santorini Colombo hazard work. The Hellenic Monitoring Network exists and functions. International collaboration between Greek, Italian, American, and broader European research institutions has produced a body of knowledge about this system that is considerably richer than it was even 15 years ago. Early warning systems in the Mediterranean, while not yet comprehensive, are being developed and expanded. What you can do with this information is straightforward. If you're traveling to the Aegean, knowing the geography of what you're visiting is simply intelligent. Knowing where evacuation routes are. In Santorini, that means getting to higher ground on the caldera rim, away from the eastern coastline. Takes about 10 minutes of research and could matter in a way that no amount of Instagram preparation could. If you live in any of the coastal communities of the southern Aegean, engaging with local civil protection information and understanding what a tsunami warning signal sounds like in your municipality is not paranoia. It's the same logic as knowing where the fire exits are. This system will continue to be monitored. The data will keep coming in. And when it tells scientists something significant, the research will be published, the alerts will be updated, and the conversation will need to happen publicly. Not buried in academic journals, but clearly, honestly, for the people whose lives sit within the hazard zone. If this video helped you understand something about the Aegean that you didn't before, or if it changed how you think about the landscapes we call paradise, that's exactly the point of making it. There's a related conversation that connects directly to what we've covered here, about another hidden submarine volcanic system in the Mediterranean that hazard researchers have been quietly escalating their concerns about. One that sits near a coastline with an even larger seasonal population. That story is coming. In the meantime, if this kind of science-grounded, honest hazard coverage is what you come here for, subscribe. Leave a comment with what you want to see covered next. The community that's built around this channel is what makes deeper, more careful coverage like this possible, and that genuinely matters.